SAMAS is a Category B research and technology project coordinated by the European Defence Agency, that is acting as contracting authority, and funded by two European member states, Italy and Poland. Focusing on the Italian side, the project consortium includes Politecnico di Milano, specifically the Department of Mechanical Engineering, that is acting as the project contractor, and the aircraft division of Leonardo Company. From Polish side, the Air Force Institute of Technology, that is a scientific and research organization, and Military Aviation Works #1. SAMAS stands for SHM Application to Remotely Piloted Aircraft Systems, and it is aimed at the development and application of structural health monitoring methodologies with a particular focus of unmanned aerial vehicles. SAMAS is the third project in a row dedicated to SHM on aerial vehicles. Unmanned vehicles are one of the new realities our society and governments must care about. In fact, the European Commission asked for the development of technology enablers for the integration of the unmanned vehicle into non-segregated air traffic management. Among them, the development of SHM systems is a mandatory step. The main objectives of the SAMAS project are, first of all, the realization of an efficient load monitoring system. The second point is the development of an impact monitoring system. And finally, the verification of SHM systems compliance with the currently available guidelines and recommendations, and the investigation of their beneficial effects on the vehicle life cycle cost through a cost-benefit analysis and a digital twin approach. At the end of the project, a demonstrator will show the operations of the load and impact monitoring systems, applying them to two structures or platforms. The first one is a carbon fiber windbox portion in a laboratory environment. Then, a small-scale drone in a real environment executing flight tests. An initial investigation was carried out to develop accurate and reliable virtual simulations. A mix between experimental tests and advanced nonlinear numerical models were used to calibrate and validate material models. The main objectives of the load monitoring system are life consumption estimation and maneuver recognition. These can be accomplished exploiting experimental measures and numerical models to provide an estimation of the aerodynamic loads and strain field during the flight. In fact, the two platforms were numerically modeled and the proper sensing technology was selected, choosing sensors based on optical sensing technologies for punctual and distributed strain measurements. The number and position of sensors and forces are defined through an optimization procedure. We studied the effect of static loads, engine vibrations, and temperature to obtain the best reconstruction performances. Finally, the sensors are installed on the real structure. The system operation is validated first in a controlled environment in our labs, then in a real environment through flight tests, acquiring data during the maneuvers with MIL-certified equipment mounted on board. The system can reconstruct in real time a correct set of aerodynamic forces that induces in the structure a strain field coherent with the actual flying condition. The results are confirmed by strain gauges installed in a specific validation positions and comparing the strain and displacement fields with those obtained with the computational fluid dynamic analysis. The main objective of the impact monitoring system is to identify unexpected impacts and the related damages. A dual sensor network composed of piezoelectric elements and optical fibers acts in both passive and active way to characterize the impact. We can divide the system into three parts: a passive impact monitoring, a numerical module, and finally an active damage monitoring. An initial investigation was carried out to choose the sensor network optimal configuration, while the algorithms are trained with non-damaging impacts using a dynamometric hammer, then hitting the structure with falling masses, and finally shooting with projectiles. The damages are then measured with non-destructive techniques. The passive part detects, locates and reconstructs the impact force, exploiting data-driven techniques and genetic algorithms. The operation of the system is validated, comparing its result with the experimental information, showing its ability to fully characterize an impact event. Then, the numerical module gives an indication about the damage extension, leveraging on a building block approach for the simulation process to build a reliable and efficient virtual test environment that is able to mimic the behavior of the actual structure. The results are experimentally validated through a comparison with actual damage dimensions. The active part verifies the damage presence in the real structure. Piezoelectric elements excite ultrasonic waves that are used for the calculation of a damage index that is representative of the actual structural health state. Finally, we installed the system on the Wingbox and validated its performances in real time, shooting the structure with projectiles. We are confident that our project will contribute to implement this system directly in the real world.